Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. So we are given a problem here. This problem is on global register allocation. Basically, register allocation happens when for a given piece of code, like any given piece of code which you might be having in your C++, Python, Java, whichever high level language, the compiler sits in between your code and machine, right? So this compiler needs to translate the code from the English language which we write in to a machine level code, or you can say a binary or low level language, right? So this language is not understood by humans. This is only understood by machines, and if you come from a science background, computer science background, then you might recognize this as inputs given to flip-flops and other uh, basic components of the circuit or motherboard that a computer has. So we'll not dive into those things here. What we need to know out of this is, in the code we have variables, right? In the code we have variables. So those variables and their values are stored in the memory heap or stack, which you might say, right? Stack. So in order to process this data which lies in the stack, this needs to get passed into another storage, which is register, which lies closest to the CPU and is the fastest storage system in a computer architecture. So for that reason we need to have these registers. And one more important thing which might be useful for this video is, registers are like the most cheapest component most expensive component in the storage department of a computer system. So since it is the most expensive, so the quantity will of course be less, so that the entire cost of system is affordable by the common user. So what we found out in this explanation is, the number of registers needs to be less, right? But for a program to have for a program to be quite efficient, or you can say the regular program which a user writes, it has, the number of variables is too huge. You might argue that for a simple calculator program the variable is hardly under 10, but for a complex system or a complex software design, there might be thousands or even lakhs of variables in the code. So all those variables need to pass on this particular system, that is from memory stack to register, and inside the register the value has to be changed by the CPU, by the flip-flops, and then we get the final result, and it gets again stored in the main memory. So this was a backdrop or a prologue of what we are going to discuss. So now let's go to the question itself. So given the following CFG stands for control flow graph. Okay, the diagram is displayed below. I will show it later. We need to perform global register allocation and two physical registers R1 and R2. So as I mentioned, the number of registers is limited in a system. So here also in the question we have only two registers, and we need to compute the spill costs, live ranges, and conflict graphs. Assume the cost of load is equal to 2 cycles, cost of store is 1 cycle, execution frequency of basic blocks is this. So we'll discuss all this in detail in later stage of this video. So first thing is, what is this global? So global register allocation is when we have a code, right? And for that entire code we need to perform the register allocation. There might be cases that our code has some modules in it. Okay, let me erase this so that we can use this space. Okay, so just as I mentioned, our code might be consisting of functions or modules, and those modules might be using some uh, variables, you can say. So those variables need to be stored in the registers only, right? All the operations which we perform has to be gone through registers, and in that case, these allocations which are pertinent to the module itself, that there might be like 10 variables here, there might be 20 variables here, there might be 5 variables here, there might be 15 variables here. So the register allocation which happens for a single module or a single function which is inside the entire code, that is called local register allocation. But don't worry, we'll not be touching on that in this video at least. And what we are going to talk about is the register allocation for an entire main program as a whole, right? So so this is what we are going to talk about, and let's first figure out what is the details that are given to us. So first is the cost of load. So whenever we need to load a particular data from our memory in main memory to the registers, as I mentioned, we need to consume some CPU cycles. As you know that CPU runs in a clock that is 2.5 gigahertz, or these days computers have even higher frequencies for that. So this is the cycle speed of a CPU. So each time the CPU runs a check over the processor, it has to execute, it follows this particular speed. So in our question we are given that the cost of load is 2 cycles, and the speed is not measured for a process in terms of gigahertz, rather it is measured in terms of cycles. So this is what 2 cycles means. Similarly, cost of store. So whenever we are going to store a value from register to the main memory, it also takes time, right? Since the vice versa, as we discussed above, from main memory to register it takes 2 cycles, and from register to main memory it takes 1 cycle. Perfect. So now we come to the next part. We are given the frequency. So frequency is what? Frequency is basically the number of times you can relate it to loops, for loop, while loop, things like that. And basically when we are executing a particular piece of code more number of times, that is not only once but a lot of times, then we call it as the frequency of this basic block. Okay, so in our case we are given basic block 1 has 1, basic block 2 has 0.5 and 10. So okay, so this is the data that we are given. Then first thing we need to consider that we are only given 2 physical registers, right? Registers. So first thing that should come to our mind is it at all possible to convert our program which we have given in this particular control flow graph? Is it at all possible for 2 registers to accumulate all this data and proceed with the working? So if it fails this, then we will directly say that okay, the program will not execute with 2 registers, we need to have more than 2 registers. We'll find it out in just a minute that how we will determine whether it is possible or not. So the control flow graph which is given in the question is this. So in basic block 1 we have DEF. DEF stands for definition, right? Definition is when we define a particular variable with a given value. This value has to be given from the user input, right? Or either it can be fetched from the main memory itself. So this is definition. And use stands for basically emitting the value to the user console, or displaying the output, or basically loading it back from memory to register, you can say. So this is what basic block 1 is, and it has def E, def A and use E. So then the control moves to two parts. You can see that it goes to basic block 2 and basic block 3. In basic block 2 we have def b, def d and use b. Similarly we have some statements in bb3, and once it happens in both these basic blocks, we go back, we now go to the basic block 4, right? We go here. Okay, so the first thing which we might want to clarify in this here is there is a concept of live in and live out. So live in technically means the number of registers defined in the previous or predecessor basic block, and live out stands for the number of registers defined in the successor basic block. Don't worry if you don't understand this, I'll explain it further down. So then we have another thing called live range. So live range is the basically sequence. This is a sequence of basic blocks through which a virtual register remains alive. As I mentioned that the number of actual registers in a system is limited, we need to consider virtual registers while building our code in order to build the code efficiently from a programmer's perspective, and then we can optimize it with respect to the machine. Okay, so this is live range. Then we can redraw the graph, right? We can use this definitions and try to calculate the live in, live out and live range for the variables. So this is basic block 1, and in basic block 1 we can see that there is no basically, as we saw, there was no register that was previously occupied from here because this is the start of our program. So there are no registers basically needing before this, right? So it is 5. Once we pass through this particular basic block, then we have live out A. So why this live out A? You might say that because we have a definition A here, and we see that A is being used in bb3 as well as bb4, right? So this A has come from basic block 1. So since this A has to be fetched from basic block 1 and then used in basic block 3, we will have the live out A. Why? Because this A will now move away from or out from basic block 1. So this is live out. Similarly, since it will move out of basic block 1, it has to enter as well. It has to make its way inside bb3. So then it comes as live in A, right? Similarly, in basic block 3 it will execute, and then again you might say that in basic block 3 we have definition D, and then we have used it in basic block 4. So similarly we will have live out A and D because A has to be now moved outside of basic block 3, so it will come here, right? Similarly we will have live in A and D, right? And one important or interesting thing you can say is, even though A is not used in basic block 2, it will still be passed as live in this part, and then it will go as live out in this part. Although it is not used here, but we will follow this because we need to use A in basic block 4, which is a connection of basic block 2. So after we find out the control flow graph for this, we now are good to go with the next part, that is conflicts. So since there are only 2 physical registers, so assigning values to them can give rise to conflicts, and let us see how. So this is the live ranges, you can say the live ranges of all the conflicting variables. So I have mentioned them in a particular sequence in which they occur in this given control flow graph, right? So if we see, first definition A occurs, then use A, then def B, then use A again, then use B, then def C, use A and use C. So live range, as I mentioned, is the set of sequence of basic blocks or statements through which a virtual register is active. So you can say that def A occurs here, and the last usage is this, right? So the entire part will be covered with the live range. Similarly with B, the first def occurs here and the last use occurs here. So the entire live range will be this. Similarly for C. So we can see that whenever two of these lines, like let me change the color, these lines intersect, right? So there is a conflict. Similarly, we can see that here is a conflict. This means that the variable A is in conflict with both B and C, or you can say they are both overlapping at a place. Now we need to check that whether it is possible for two registers to assign all the variables in a conflict or not. So we see that this particular line crosses only two red lines. It means two variables are being overlapped and we have two registers, right? So it is good to go here. Similarly, the green line passes only two red lines, so it is good to go here as well. But if it had been more than two, let's say we have another, say here, then it will not work and we will say that okay, two registers will not do the job in our case, right? But that is not the case. Let me erase this. So I hope you understood what is live range and how we need to determine it. So next thing we need to this was the live range part which was asked in the question. Then we need to draw the inference or conflict graph. This graph basically helps us determine the relationships between the variables and even if and helps us to check whether there is a conflict between them or not, because as you saw here, marking the live ranges and checking for conflicts can be a bit tedious and unclear to understand. So we draw like this. So we can see that there is a conflict between A and B from our this live range part. So there is a line between A and B. Similarly between A and C. So since the degree of a particular node in this graph is less than 3, means we can use two registers to basically assign these values variables a value, right? If it had been suppose A, D, B and C, then we would fail to assign two registers to all the variables at the same time. We cannot do that, right? Because then we would have no, sorry, I made a mistake here. Let me erase this. Suppose we have this particular edge, right? And here in this case, suppose we color this with red and we color this with blue. Then we cannot color this with blue or red. We need to choose any other color, say third color. So in this case, this is a more than two colorable graph. So since this is more than two colorable graph, we need to have more than two registers to basically allocate to the variables. So I hope you understood what I tried to say here. So this was the inference or conflict graph that we'll be drawing here, and two registers are sufficient since this is a two colorable graph. Now we come to the register allocation part. So in here we see that first we need to load E. Load, as I mentioned, stands for the loading of data from memory to registers. So we are loading the memory location E to R1, then we are loading A to R2, then we are using R1, we are using E again, so we are emitting it. Similarly, we will be loading B with R1. Now you will see that we have just used R1 right away because the E is not used anywhere else, right? E is not used anywhere else in the code, so we will not bother about keeping E back into the memory. So we'll just basically load B into R1. And why not R2? Because R2 is already containing A, so we will not use A. We will not disturb A and we will just keep R1 engaged. Then we need to store B, because since A has to go along and B can be retrieved again, so A will keep its place in R2, and then we'll just store or empty the register R1 and store into B, which is another location on the main memory. Perfect. Now we go to the next step, which is load D. So we'll load the memory address D into R1. You might see that here also R2 is remains undisturbed. Then we come down, then we again load B, right? Just as we had in the control flow graph here, we were here, we loaded D, then we need to use B, so we will again load B from the memory location we stored into R1. So we loaded B into R1 and then we emitted R1 because we used that. Okay, now in the basic block 3, we will load C into R1, we'll emit R2. Why R2? Because we are using A here. So again the same thing, we will not disturb A anywhere in this regard because A has to be passed through this basic block and used below. So we'll emit R2, we'll then emit R1 because we needed C, and then we'll load D into R1, right? And once we do that, we come to the final basic block, which is basically use A and then use D. So what we'll do is we'll emit R2, and now you'll notice that we are loading D into R1, right? Why we are doing this is because in this particular place B was stored, sorry, right? Here although D was stored, but since both the controls are coming to basic block 4, we need to ensure that R1 contains D. So we'll load D into R1 and then we'll emit R1. Perfect. So I hope the register allocation which was asked in the question is now clear to you. Now we come to the next part. The next part is the spill cost. Spill cost is what, since each time you load or store a value into the memory or back into the register, you are using cycles, right? And cycle means time. That time is basically the spill cost. Sorry, I made a spelling mistake here. Spill cost. So that time which is lost in the intermediate work, because this is not what the program says you to do. The program says you to perform the calculation which the CPU does, but all this intermediate IO, you can say, or the transfer of data from memory to register is being done to support the program. So that is the spill cost, right? So what we will do here is we will, before further we discuss what is spill cost, I want you guys to pay close attention here, because this you need to remember by heart, right? This here denotes def, that is definition. We need to link this to the cost of store, and we need to link use to the cost of load. Let me use another pen. We will link def with the cost of store, and we'll link use with the cost of load, because these two are different terms, so one might get confused while dealing with this. So in order to ensure that we remember, we will just keep this in mind. Okay, now we will we'll see two formulas. These are important formulas. So cost of definition, suppose we need to basically define a particular variable and then store it into the memory. So what we need to do, we will need to add up the cost, spill cost, for this particular definition, right? So in order to do that, we'll just multiply the number of defs, that is the number of definitions for that particular variable, execution frequency of the basic block, and the cost of store. As you can see that defs was linked to store, so that we will use store here. Then we will find out the cost of use, which is the number of times used for a particular variable, execution frequency of the basic block, and cost of load. Don't worry if you didn't get it, I will explain it with an example so that it makes much sense and becomes clear to you. So now we'll come to the next part. So since this will be calculated per variable, right, each variable will have its own spill cost, so we'll calculate it. So first for A, the variable A, we will sum the spill cost over all the basic blocks, because each basic block will have its own defs and use, right? So we'll need to add up that for each basic block. So let us consider the first basic block. So in the first basic block, what we need to find is number of cost of defs, right? So number of defs into execution frequency of BB into cost of store. So let's first see what was it. Okay, so the cost of store is 1 cycle, execution frequency of BB is 1, BB2 is 0.5, and BB3 0.5 and 10. So I'll just tell you guys to note it down somewhere so that we will use it in the numerical. Okay, so we'll just go back, and I want you guys to write down this as well so that we will use it again. So in this we see that first is def, right? So def will be considered and there is no use, right? So in this particular basic block there will be only one term for def. In basic block 2 there will be no spill because A is not involved. In basic block 3 there will be only one case, that is use. And again in basic block 4 there will be one for use A. So there will be all total 3 terms, right? So 1 into 1 into 1. 1 is the number of defs, which is 1 for basic block 1, into execution frequency of BB1, which is 1, and cost of store, which is also 1. Then we come to basic block 3. Its number of use is 1, the execution frequency is 0.5, and the cost of load is 2. Then we come to the basic block 4. The number of use is 1, execution frequency is 10, and the cost of load is 2. When we add these up, we get 22 cycles, which is the spill cost for A. Then we come to B. It has been used only 2 places. One is basic block 2, I guess, and one is in basic block 3. So 1 into 0.5 into 1, which is the def in basic block 2, and 1 into 0.5 into 2 for usage in basic block 3. So it comes out to be 1.5 cycles. Similarly, we will have for C, which is used in basic block 3, and I hope it is not used in basic block 2, right? It is used in C, and there will be 2 terms, one for def and one for use. So let's have a look at that. Yeah, 1 into 0.5 into 1 for the def, and 1 into 0.5 into 2, 2 is for load, it is for 1.5 cycles. So then we come to D. D has been used in many places, in basic block 2, basic block 3, and basic block 4. So for that we have the corresponding frequencies, and since only one time it is used, so 1 into all places, and only this it has load, so there are 21 cycles. Lastly, for E there will be 3 cycles in the similar manner. It is only used in BB1. So you can basically add all these cycles. I think it will come out to be 6 plus 21 plus 22, so it is like 43, 49 cycles in total. So if it is asked for the total spill of the entire program, then it will be, I think I calculated it right, yeah, it will be 49 cycles. So 49 cycles total spill cost. So this is it. So I hope I was able to make you understand how we need to calculate the global register allocation for a given control flow graph and any given program, I would say, because that can be converted into a control flow graph. And if you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then please give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.